Hello, this is Dr. K. In this video, we're going to talk about sorting and searching, but we're not going to get into the details. I'm just going to give you an overview of two sorting algorithms, insertion sort and merge sort, and two searching algorithms, linear search and binary search. We'll also talk a little bit about complexity. Let's get started. The complexity of an algorithm is an indication of how long it takes that algorithm to run in terms of the size of its input. For the algorithms that we'll be looking at in this video, the input will always be some sort of sequence, like an array. Therefore, the input size will be the size of the sequence. Complexity is traditionally discussed in terms of big O notation. This table gives you the most common big O notations that you generally see, from fastest to slowest. It also gives the name of the complexity level and examples of algorithms whose runtimes have that complexity. The top row shows big O of 1, which applies to algorithms that run in constant time. Constant time means runtime of the algorithm does not actually depend on the size of the input. It's just constant. Whether you have a 10-element array or a 100,000 element array, an element of either array can be accessed just as quickly. Insertion and deletion of nodes in a linked list is also a constant time operation. However, searching for a node to insert or delete is not a constant time operation. It takes linear time. The next complexity level in the table is big O of log n, or log n time complexity. Log n time occurs anytime you are working with a binary tree and you just need to do something once in each level of the tree. This describes the binary search algorithm that we'll talk about later in the video. Linear time algorithms are very common. Anytime you iterate over a collection to find an element or perform some sort of calculation using the elements, you're doing something that takes linear time. The next level of complexity is log linear. The best sorting algorithms take log linear time. We'll look at the merge sort algorithm later in this video. The next complexity level here is quadratic, or big O of n squared. Anytime you see one loop nested inside another, there's a good chance the algorithm takes quadratic time. Insertion sort is a good example of this. The next complexity level here is just a generalization of quadratic. It occurs when the complexity is big O of n to the k for some positive integer k. Algorithms with this complexity are called polynomial time algorithms. In fact, since all of the complexity levels before the red bar can either be expressed as a polynomial or can be bounded by some polynomial, computer scientists generally refer to all of them as polynomial time algorithms. The algorithms after the red bar are generally referred to as exponential time algorithms. These have a runtime of the form big O of k to the n for some integer k that is equal to or greater than 2. There are some well-known problems for which only exponential time algorithms are known to exist, like the traveling salesman problem, for example. This is troubling for a lot of computer science researchers because exponential time solutions take far longer than polynomial time solutions when the input gets large. We'll take a look at this in the next table, but before we get there, I just wanted to say something about factorial time algorithms. They do exist, but in general, they're very rare. I just put this one up there to indicate that there are classes of problems that theoretically have a greater complexity than even exponential time problems. In general, though, the important distinction is between polynomial time and exponential time problems. Let's look at the distinction between these two classes of problems. Polynomial time, which is n to the k, and exponential time, which is k to the n. Remember, k is some positive integer, and n is the size of the input. Let's assume we have 5 algorithms that each have a different complexity. The first algorithm runs in linear time. The second algorithm runs in quadratic time, and the third algorithm runs in polynomial time with a degree of 5. So the first 3 are polynomial time algorithms. The fourth algorithm runs in exponential time with base 2, and that's the most common kind of exponential time algorithm you will see. The fifth algorithm runs in exponential time with base 3. We're going to look at how much time these algorithms take with inputs of different sizes. For the purposes of this example, you can think of the input size as the length of an input array. We're going to assume that each simple operation takes 1 microsecond to complete. And 1 microsecond is 1/1,000,000th of a second. Consider the first column, where the input size is 10. The linear algorithm performs 10 simple operations. Each simple operation takes 1 microsecond. So the total runtime is 10 microseconds, or 0.00001 seconds. The quadratic algorithm performs n squared simple operations. It ends up taking 1/10,000th of a second to run. The n to the 5 algorithm ends up taking 1/10th of a second to run. The exponential 2 to the n algorithm takes 1/1000th of a second. And the exponential 3 to the n algorithm takes about 0.06 seconds to run. Here's where it starts to get interesting. I'll give you 5 seconds to look at these numbers and tell me, for an input size of 10, which of these algorithms is the slowest. Okay, you just need to look at them and you can see that the n to the 5 algorithm is the slowest for an input size of 10. All right, before we go on to fill out the next column, I want you to do something very important. I want you to get out a piece of paper and write down the units of time, like seconds, minutes, hours, and so on, that you think will appear for each complexity level when we increase the input size to 20. I want to emphasize that you should not calculate any of the runtimes. I just want you to use your gut instincts and tell me what the units of time will be for linear, quadratic, n to the 5th, exponential, and 3 to the n when the input size is increased to 20. For example, will they still all be seconds? Right now they're all seconds. Will any of the runtimes increase to minutes? Will any of them increase to hours? That may seem unlikely, but what's your gut feeling? Please pause the video and indicate what you think the units of time might be for each one of these algorithms when the input size is 20. I'll give you 10 seconds to pause the video, starting now. Okay, are you ready to reveal the next column? Let's take a look. Interesting. Of course, the linear algorithm is still the fastest, but the slowest algorithm is now the exponential 3 to the n algorithm. And it is slowest by a lot. it will take 59 minutes to complete. That's almost an hour. The previous slowest algorithm, polynomial n to the fifth, is now in second place, but not by much. It's taking about 3 seconds, while the exponential 2 to the n is taking 1 second. Okay, hopefully that was enlightening. Now, armed with your refined intuition after seeing this column, let's play the same game again with an input size of 30. But this time I'm going to go down the columns with you. Will the linear algorithm still be seconds? Yes, it looks like the linear algorithm will definitely still be seconds. In fact, it looks like the linear algorithm will be exactly 0.00003 seconds. What about the quadratic algorithm? Again, it's pretty easy to see that the quadratic algorithm will still be seconds, and you might even guess that it will be 0.0009 seconds. The end of the fifth algorithm is a little harder. Will it become minutes or perhaps hours? What do you think? What about 2 to the n? Will it be in minutes or will it be hours? Surely our 3 to the n algorithm will be in hours, if not days, right? Would anybody say weeks or months, years? Okay, I'll give you 10 seconds to think about this and pause the video if you want, starting from now. Okay, let's see how close you got to the correct answers. Now it looks like things are getting interesting. An input size of only 30, imagine that, an array with only 30 elements. Our linear time and quadratic time algorithms can still be counted in microseconds. Our end of the fifth algorithm has not gone over half a minute yet. But our exponential 2 to the n algorithm is taking almost 18 minutes. And our exponential 3 to the n algorithm is taking 6.5 years. That's right. How would you like to wait for 6.5 years for an answer when you only put in an array with 30 elements? Okay, hopefully you've learned something from the last two reveals. It's time to guess the time units for the last column. And please note that the last column has an input size of 60. That's double the input size of this column. We're not just adding 10 anymore. So let's run down the columns quickly. I think it's obvious by now that our linear and quadratic algorithms are still going to be well under a second. Our end of the fifth algorithm, it may get to minutes, but will it get to hours? And how about our intractable exponential time algorithms? For 2 to the n, will it be hours, days, weeks, months, or even years? What do you think? And that 3 to the n looks even scarier. If it's already taking 6.5 years to complete for an input size of 30, will it even be finished in our lifetimes for an input size of 60? For that matter, will it be finished in our grandchildren's lifetime? If you need it, I'll give you 10 seconds to pause the video and think about this a little longer, starting now. Okay, did you make your guess? Let's see what we have. Wow. Linear time and quadratic time algorithms, still just a fraction of a second. End of the fifth algorithm, under 15 minutes. Not great, but go fix yourself a sandwich and it might be finished by the time you come back. But how about those exponential time algorithms? 366 centuries, even for the 2 to the n algorithm. That's centuries, not years. And then there is the exponential 3 to the n algorithm. You give it an array with 60 elements, only 60 elements, and it will take you 1.3 times 10 to the 13 centuries to get the answer. Will the Earth still be around then? Can we just assume that the answer is 42 or something like that? Well, the future does not look good for exponential time algorithms. And that is why such algorithms are called intractable by computer scientists. Theoretically, they may produce a solution, but practically, we're not going to see it.